Worksheet D. I put all the solutions on Blackboard with the answers, and then I put a page of the solutions. And you said we're where?
14.
14? Some of the ones on the back page got to be pretty boring. Because you kept doing the same junk over and over and over. Well, let's do 14 anyway. So we're doing the integration review, which is section 7.5. And we're on problem number 14. Like I said, I was getting tired of doing partial fractions. And this looks like a prime candidate for partial fractions because it's not a u du integral. If we take u to be the denominator, I get 2x plus 6. And there's no way to make 2x plus 6 look like a something times x minus 1. So it's not a u du integral. So we attempt partial fractions because we've got a polynomial over a polynomial. See if I can see what I'm writing. X squared plus 6x plus 9 does indeed factor. Factors of 9 that add to 6 would be 3 and 3. So this factors as x plus 3 all squared. So you can do partial fractions, but I'm going to do this by attempting a double substitution. I'm going to let u be x plus 3, so that du becomes the dx. So I've got something for this and this. Then we'll get something for x by going back here and writing x as u minus 3. When I put that back in here, I'm going to have a function of u. I'm going to look at it and see if I can integrate it. So like I said, x was u minus 3, so I put u minus 3 right here. Then I've got to subtract that 1. Then the x plus 3 was u, so I've got a u squared down here. And dx is du. So my numerator simplifies to u minus 4, and all of that's divided by u squared. Does that look like something you can do? How do I proceed from here?
Split the fraction.
Split the fraction. I've got two fractions with a common denominator of u squared. So I can write that as u over u squared minus 4 over u squared. Simplify a bit, and then I can integrate. So what I'm going to integrate is the 1 over u minus 4u to the negative 2. And this gives us a logarithm. Here, if I add 1 to the power, I'm going to get a negative 1. We have to divide the negative 4 by negative 1. So that gives me a plus 4u to the negative 1. And then finally, each u is x plus 3. So we put the x plus 3's in there. And our final answer is the natural log of the absolute value of x plus 3. And I'm going to put this on the bottom underneath the 4. Put the x plus 3 under the 4, plus our arbitrary constant. So if you did partial fraction decomposition, you'll get the same thing. I just thought for a little variety, I can show you maybe a quicker way of doing partial fractions. And this double substitution typically works when you have a first degree inside and a first degree outside, as long as it's lined up correctly for you. Yep, it should be x plus 3. I don't know where the 4 came from, probably from the numerator. Unduly influenced by that 4 on top. Do you have much practice doing integrals with a double substitution? There were some back in section 7.1. If you need some more practice, grab some out of the book. All right, number 15. (15, 16, and 17 are all close cousins of one another. They all have essentially the same denominator. In number 15, the denominator is by itself, x squared plus 6x plus 14. In the next problem, the square root sign is above it, and in the next problem, that has a different numerator. So let's see what the one upstairs makes a difference. It's clearly not a UDU integral because I don't even have a numerator that involves any function of x. So I'm going to try to do this by, I don't know, you tell me. If I can't do a UDU, I try partial fractions. But then I'm looking for factors of 14 that have the same sign that add to 6. Got any? No? 7 and 2 add to 6? 7 plus 2 is 6. Welcome to Thursday. So if we can't factor it, what do we do? Yeah, that thing. Oh, I don't want to find zeros, right? I want to be able to manipulate this so I can integrate it. Complete the square. Complete the square should be in your bag of tricks for things that you don't know how to factor. So we're going to complete the square on this. So let me complete the square right here. I got to add a number and then take it back out. And then add that 14 on the end. And the quick trick is to take half of the middle number and then square. Half of 6 is 3. 3 squared is 9. Put a 9 here and a 9 there. So now I can find factors of 9 that add to 6. Those are going to be the 3 plus 3 like we had in the last example. Then these two numbers add to 5. So now the integral looks like 1 over x plus 3 all squared plus 5. So I'm comfortable with that integral. It looks like one I know. Do you recognize it? Not even that hard. That's an arctangent. That integral up there looks like the integral of 1 over u squared plus a squared du, which is 1 over a arctangent of u over a. Our u is x plus 3, du is dx, just like in the last example. And the a term is square root of 5. So we should get 1 over square root of 5 arctangent of x plus 3 over the square root of 5, and then we're done. So completing the square will often give us an arctangent integral, as long as we have a plus sign here. After we do this, completing the square. If we had a minus sign there, then we do the trig substitution. Now let's do the same problem, but put a square root sign over the denominator. So we do the same two steps. We recognize it's not u du. So we think, well, let's complete the square and see what that looks like. Now when this is under a square root sign, it's no longer an arctangent integral. The arctangent integral has no square root sign. So we don't do this step and don't jump to that solution. Now we'll do a trig substitution. I want to get rid of the square root sign. So I think of a trig function whose identity would suit that. Which one has the plus sign in it? Which trig sub? I'm going to take the variable to be the tangent, right? So we're going to let x plus 3 be the tangent of theta. Because I'm hoping to use the fact that the tangent squared plus 1 is secant squared.
That's square root of 5 tangent theta.
It is square root of 5 tangent theta. Thank you. I need to get rid of that 5 after I square it. So that x plus 3 squared is 5 tan squared theta. And then I can factor the 5 and use this. But I need a dx, which we don't just make a straight substitution. We have to go through here and take the derivative. Pull down the constant. The derivative of tangent is secant squared. And there's my dx substitution. Square root of 5, secant squared theta d theta. So let's put it in. And this is going to look like 1 over, I'm squaring this and getting 5 tan squared theta, plus the 5 on the end, all under the radical. Dx is all of this. When I factor out the 5 right here, there's my identity that I'm going to use the secant squared. So the radical in denominator has the square root of 5 secant squared theta in it. And I still have that stuff up on top. So we take the square root of both those terms and get a square root of 5 secant theta in the denominator. So the square root of 5's cancel, one of the secants cancel, and I'm left with just an integral of a secant. Remember that one? The integral of secant theta?
I'm not sure what the secant theta plus tangent theta.
Perfect. And then we're going to go back over to the original substitution and get functions of x for those two trig functions. So I'm here, solve for the tangent of theta, and get x plus 3 over the square root of 5. And so it's my angle theta right there. Tangent is the opposite over the adjacent. So we got x plus 3 here, square root of 5 there. Leg squared plus leg squared is hypotenuse squared. Gives me x plus 3 squared plus 5 under the radical is the length of the hypotenuse. The secant is the ratio of the hypotenuse to the adjacent. So I'm going to replace this with that long radical divided by square root of 5. Tangent of theta is x plus 3 over the square root of 5. And so we get as our final answer the x plus 3 squared plus 5, all of that under the square root sign over square root of 5 plus x plus 3 over the square root of 5. So without the square root sign, the sum of squares is an inverse tangent. With the square root sign, it's a trig substitution. So in problem 17, a different numerator is up there, a function of x. So let's see what happens if I put the 2x plus something up there. 2x plus 3. Put a 2x plus 3 up there. No square root in the denominator. Right, no square root in the denominator. So go back to here. So I make a check again to see if I have UDU. The denominator is 2x plus 6, so I don't have the 6 there, so it's not UDU. I can try the completing the square thing again, and I get the x plus 3 squared plus 5 in the denominator, so let's look at that. Because I would be attempting to do partial fractions, I can see it doesn't factor, so I complete the square. That's my train of thought here. I don't have a radical sign, so there's really no sense in doing a trig substitution. So we're going to look at this a little bit harder and see what we might want to try. So I'm waiting for you to chime in.
Can we try to make a numerator to 2x plus 6 and do negative 3 over x plus 3 squared?
I like that idea. Let's take the 2x plus 3 and write that as 2x plus 6 minus 3. And so if I have this over that denominator, it's a UDU problem. If I have this over that denominator, we saw how we could make that an inverse tangent. So just kind of put what you needed here. We needed the 2x plus 6 to make the UDU. And then the 3 by itself gives us the problem we had a second ago. Okay? So is that too sneaky? All right, so we'll do that. And then we'll split up the numerator. We'll write that as 2x plus 6 over the x plus 3 squared plus 5. And then we'll put the minus 3 right there and have a 1 over x plus 3 squared plus 5. So this integral we just did, that one was the arctangent integral. This integral, we're going to take the whole denominator to be u, and then its numerator is du. So that's now a 1 over u integral. And then again, I said we did this one a second ago as an inverse tangent. That one had the 1 over the square root of 5, arctangent, of the x plus 3 over square root of 5. So that gives us a logarithm, and it'll be the logarithm of this. So sometimes splitting the numerator is helpful, but you've got to maybe doctor the numerator up a little bit by adding 0 so that when you split it up, you can get 2 integrals that you can do. Okay, so let's get away from that particular fraction. Number 18. We got 3 sine of x up here. Cosine squared of x minus 9 dx.
I think it's a plus 9.
It's a plus 9. That makes it easier. Plus 9 becomes easier. Thank you. So who wants it? Why is the plus 9 easier for me? It's an arctangent, right? You've got a sum of squares in the denominator, and the u term then is the cosine of x. If you've got cosines and sines in your integral, u du is almost always going to work. Just take u to be the cosine. Don't take the whole denominator, just the cosine, so that you'll have an arctangent integral. If u is equal to the cosine of x, du is minus the sine of x. So I'll put a minus sign out there and get the 3 out of the way by pulling it out. So we're going to have minus 3 out front. Then this is du over u squared plus 9. And there's your arctangent integral. So you get 1 over a, arctangent of u over a. Our a term is 3. 1 over 3, arctangent of u over 3, but our u is the cosine of x. So I'll go ahead and put that in. You can cancel the 3's if you want. Minus the arctangent of the cosine of x over 3. Hot? Yeah. I don't know if moving this switch does any good. I think it automatically goes back to where it was. Oops, I just turned it up.
The outside thermometer was set to 74 degrees the whole way.
I said 74 degrees. I said 76 actually. It's your body heat. You guys bring less warm bodies in here. Cold showers in the morning. Okay, let's see what number 19 says. Oh, number 19 is the one that you like. What was that? What was that little snide remark? Finally, 19 problems later, I get to one you like.
It's time to build the table.
There you go. Everybody likes integration by parts using the table. Don't you wish you invented that? You know it's going to be a tabular form of integration by parts because I got polynomial times trig, and the power on our polynomial term is 4th degree, so we've got 4 integration by parts here. Quickly do that in a table. given the choice, the polynomial term should be the u, because you want to run your derivatives to 0. And then the trig function is the dv. So remember that when you integrate a sine, you get a minus cosine. The 2 inside the parentheses is always going to spit out a factor of a half. So build your table real quick and see if you can do this all the way through, and then I'll catch up with you. All right, you're going to need 1, 2, 3, 4, 5, 6 rows there. You run out of derivatives. Remember again, the integral of a sine is a negative cosine. Integral of a cosine is a positive sine. And then we're going to get a 1/2 each time we integrate. And also remember keep the sign, change the sign as we alternate down the row. And we're going down the diagonal. I want you to know I had a chance of being in Kansas City tonight for the basketball game, and I said, nope, I got people. I got people I got to take care of. What? I'm bad juju. When I go up there for that conference tournament, we lose. So I thought I'd have to do my part for the team as well. But we might. We might be able to go to Indianapolis, so we'll just delay missing class for that. It's just so important to me. I didn't want to go. Didn't want to go, but I didn't want to go. Did we win the baseball game? We did win the baseball game.
Who did we play?
We played Gonzaga, who we probably couldn't beat basketball. Gonzaga. They're in Seattle, Washington. Okay, I'm integrating. Integral sign is minus a cosine, then the 1/2. All right, integrate cosine is a positive sign, and then another 1/2. Integrate sine gives me another 1/2, I said. Go to a 4. Integrate sine, and you get negative cosine. Negative 1/2 gives me a positive 1/8 out here. Another 1/2 gives me a positive 1/16 sine of 2x. and then a negative 1/32 cosine of 2x. Do we agree with all those antiderivatives? Then we do down the diagonal products. Keep the sign, change the sign, keep the sign, change the sign, keep the sign. So the first one is going to be a negative 1/2 x to the 4th cosine of 2x. Change the sign gives me a minus gives me a plus. The 4 times the 1/4 gives me a 1, x cubed sine of 2x. Next one, keep the sign. I get 12/8 x squared cosine of 2x. I'm too lazy to reduce. What did I say, x squared, didn't I? Okay, change the sign here. So I get negative 24x times 1/16. So negative 24x over 16. My trig function now is the sine of 2x. Now I'm on the positive 24 times a negative 1/32. So it gives me negative 24/32 cosine of 2x plus c. Okay? So I'll put that one on the test, and then as the bonus, I'll say, show that the derivative of this simplifies to that. Would that be something you'd want to try? You'd say, that ain't worth 5 points.
5 points?
6 points?
I'll go for it.
We're starting to bargain for bonus points? Here I was giving things to you. When somebody gives you a Christmas gift and you open it up and say, is that all? One sock? Where's the other one? You get that next Christmas. Take good care of this one. Okay, so be able to recognize them speeds things up for you. The next problem, number 20, sine of the natural log of 3x will fit right in this little spot here. All of that's divided by 2x. I don't know about you, but when I see a logarithm in my integral, I know exactly what I want to do.
Could you substitute E or something?
Oh, not even that hard. Go easier. I would substitute. I'd take that to be u, right? Try for a u du. If u du doesn't work, then we try something else. But if there's a logarithm, let it be u and see what happens. So try it. See if it clears things up for you. Take ub, the stuff inside the parentheses. There's my hint. Let me give you a few minutes to see if you can finish it. Is it working for you? What's the derivative of the natural log of 3x? Simplifies to 1 over x, doesn't it? It's 1 over 3x times the derivative of 3x gives me the 3. So it simplifies to 1 over x. And I do have a 1 over x right there. So what do I do with that pesky 2?
Pull it out.
Pull it out. Comes out as a half. So we 1/2 the integral sine of u, and then the 1 over x dx is just du. Integral sine of u is minus the cosine of u, and u was the natural log of 3x. Two-liner. There is absolutely nothing special about problem number 21, so I'll just leave that. That's your run-of-the-mill partial fractions with linear factors. So let's do 22. We've got a 6x squared minus 7x divided by 3x minus 2 inside here. It's not a u to u integral. Long division. When you see a higher degree or equal degree denominator, division typically works. So divide the 6x squared minus 7x by the 3x minus 2. Divide first. Anything you do partial fractions wise will be bogus. X squared minus 7x. So you look first term, what I multiply 3x by to get 6x squared. Looks like I'm going to need a 2x. And take that 2x times both of those and line them up. 2x times 3x is 6x squared. 2x times 2 is a negative 4x. And then I got to subtract that line from the line above it. Gets rid of the x squareds. A negative 7 plus a 4 gives me a negative 3x. That's still able to divide into that. That's going to go a negative 1 time. Take that times negative 1 and you get a negative 3x plus 2. And subtract that line from the line above it. I believe that gives you a remainder of negative 2. And so we have the whole part, 2x minus 1, plus the remainder over the divisor. So we integrate 2x minus 1 plus the remainder over the divisor. Has long division gotten any easier for you to recognize and to do? I'm asking my second semester calculus students if they can do long division. All right, here we go. This is x squared minus x. And now you got to help me out here. What's that integral going to do for you? That's a natural log. But if u is 3x minus 2, the du is going to give me a factor of 3. So I'm going to pull out a 1/3. So we have negative 2/3, 1 over u du. So our final answer is x squared minus x minus 2/3 of the natural log of my 3x minus 2. Okay?
How do you pull negative 2 over here?
The negative 2 came from the top.
Yeah.
And then I take u to be 3x minus 2. The derivative of that is 3 times dx. Solve for dx by getting 1/3 du. You're welcome. Y'all good about integrating? Any questions about web work, integration techniques, life in general? All good. Okay, I typically skip section 7.8. Section 7.8 introduces us to a new batch of functions called hyperbolic functions. They're related to trig functions, but they're also related to exponential functions. So I'll give you a brief overview and show you why we don't really need to study this section. Hyperbolic trig functions will appear in applications in physics and in electrical engineering. Any electrical engineers in here? One of them, all right. You'll see them again then. But they're all linear combinations of exponential functions. So just a quick overview of section 7.8, but we're not going to cover it, won't do any homework, no web work. We're going to omit it, but I don't want to break anybody's hearts. We're talking about hyperbolic trig functions. The hyperbolic part means it has something to do with hyperbolas, right? A hyperbola is a little curve like this. In applications, we talk about a catenary. I don't know how to spell it. C-A-T-E-N-A-R-Y. The catenary is a curve with an equation of the form a number times e to the x over a, and then there might be a plus or a minus in here. I'll put a plus. E to the negative x over a, all divided by 2. So we write that as a function like that, and it describes things like a wire that has a little dangle to it like that. Some of the applications of this things that it describes motions of waves and temperature distributions of metal. Heat a metal plate, the way the heat spreads through the metal can be described with a function related to a catenary. Sorry?
What's the denominator? Denominator said 2.
It's a 2. It's a 2. It's just the average of those two exponential functions. Right, one is a growth curve, one's a decay curve, so you got your decay and your growth when you average them. So that function itself can be renamed by relationship with our 6 hyperbolic functions. Take the cosine and stick an h on it, and you've got something called the hyperbolic cosine. And it looks just like that, where a is equal to 1. The hyperbolic cosine of x is equal to e to the x plus e to the negative x over 2. So if you're ever in class and your professor says cosh, they're not mispronouncing cosine. They're talking about the hyperbolic cosine. Put a minus sign in there and you have the hyperbolic sine. Cinch. Notice that one is the derivative of the other. Take the derivative of this one and you get that one. Take the derivative of this one and you get that one. So in our derivative rules, the derivative of the cosh of x is the sinh. The derivative of the sinh is the cosh. You'll just get each other back without changing the sign on it. If you take the hyperbolic sine and divide it by the hyperbolic cosine, you'll get the hyperbolic tangent. So we're taking this and dividing by that. All that we lose are the 2's. The reciprocal of this one is the hyperbolic secant. The reciprocal of that one is the hyperbolic cosecant. The reciprocal of that one is the hyperbolic cotangent. Then we have derivative rules. But to compute their derivatives, we just take the derivatives over here. Derivative of e to the x is e to the x. The derivative of e to the negative x is negative e to the negative x. The 2 is a constant, so we can leave it there. So that's why I said the derivative of one is the other. To take the derivative of the hyperbolic tangent, you use the quotient rule. And it probably simplifies to the hyperbolic secant squared, right? And those are all true. I don't know. Then there's bits about what the graphs look like. Then we've got some identities. In trig function, sine squared plus cosine squared is 1, but with the hyperbolics, this squared minus that squared is 1. But you can do all that manipulations with the e's and see that that's all true. If you want to integrate this, you just integrate that. So we don't need any kind of special integral formulas. Integrate e to the x, get e to the x, integrate e to the minus x, and you get minus e to the minus x. So guess what? The integral of the cosh is the sinh, and back and forth. So they're really not new functions. They're just names of functions that we've dealt with. So I'm not going to cover it. There are derivative rules, integral rules, hyperbolic identities, but they all come from manipulating e's. So if you ever get these in other classes, they're real easy to look up, and the calculus and the algebra part is real easy. Okay? So I'm not going to waste class time on that. I've been doing math all of my life, and I can probably name on one hand how many times I've used hyperbolic trig functions, and I have about 4 fingers left over. You pick the 4. So they're really not that important. There is a relationship between them and logarithms. So like if you're doing the integrals that we've been doing, we've got these logarithms of these fractions, like sine, the secant of theta plus the tangent of theta. There's a relationship between these. So when you Google the solution and you see these goofy guys come up as your answer, there's an identity that relates these hyperbolics to logarithms of trig functions. So that way at least you know what the heck happened. So we're skipping this. That's the last section of chapter 7. No, it's not the last section of chapter 7. We've got section 7.7. We're going to take our integrals and our interpretations of our integrals. We're going to look at definite integrals that have a couple of problems. One problem is a definite integral in which one or both of the limits of integration become infinite. That's going to be a type 2 improper integral. And then we're going to look at integrals where the integrand has a problem. And those will be our type 1. So skipping section 7, 8, but we are covering section 7. And that's going to be improper integrals. We have definite integrals, and I don't know what I was going to say. I just lost my train of thought.
Is there
Right.
7.6?
7.7. 7.6 is a section on differential equations, how this stuff relates to differential equations. And you guys have a whole course in that. So I'm not going to do the 7.6 because it's just a itty bitty teeny part of the whole course you're going to get. Anybody doing differential equations next semester? 3350? Yeah. It's the end of the road for you? What you going to do, Cal 3?
Are you supposed to take Cal 3 before taking differential?
Differential equations only has a Cal 2 prerequisite, but it's to your benefit to take Cal 3 first, because you'll see some of the same things in both courses. But a lot of students will take them together, Cal 3 with differential equations when you're in a hurry. Like, why are you in a hurry? You want a job and make money? You know what getting a job means? Working, like a lot, like a whole lot. Okay, so back to section 7.7. So again, 7.6 we skip. That's differential equations. I used to always teach this, and then one semester I taught differential equations, and not one of my students remembered this. So I thought, what? So I skip it now. And then section 7.8, the hyperbolic trig functions we skip. Section 7.7, we look at improper intervals. How do I want to start here? How do I want to start? Find the area beneath the curve y is equal to 1 over x squared above the x-axis to the right of the line x is 1. So we draw a picture. Y is equal to 1 over x squared is a hyperbola in the first quadrant. I'm asking you to find the area x is 1, we'll put here. I'm asking you to find that area right there. It is unbounded on the right.
So it's starting from infinity.
I'm sorry?
So it's gonna have infinity as well.
Yeah, I'm going to ask you to integrate from 1 to infinity. We think, well, that's a waste of time. If it's unbounded on the right, there's always area added in there. Right? If you think about the Riemann sum, we're going to still add little rectangles forever and ever and ever and ever. So it looks like the area is going to be infinite. But it's not. What we're computing is this definite integral. And this is called an improper integral. This is an example of an improper integral of the first type. type 1 improper integral has some continuous function in here, and either the upper limit is infinite or the lower limit is infinite, or both are infinite. One or both the limits of integration are infinite, and the function f of x is continuous in that interval. Sometimes these integrals represent a finite area of an infinite region. Sometimes they represent an infinite area of an infinite region. If I can compute this integral and get a value, a finite number, then we say the integral converges to that value. But if I compute this integral and the value of the antiderivative is infinite, then we say that the integral diverges to infinity. In order to compute it, we have to fake this integral out into thinking it's a proper definite integral. So I just do that pretty easily. It's really easy to fake out an integral. They're just as dumb as a rock. You stick a vertical line in here. Maybe that's that little color that doesn't work. Stick a vertical line in here somewhere and cut it off. Say that that's x is equal to capital N. You compute the integral from 1 to capital N, get the antiderivative, evaluate it at the two endpoints, and then take that and move it to infinity after you compute the integral. So our steps are these. To integrate from 1 to infinity, 1 over x squared dx. I first integrate from 1 to n. And then once I get that antiderivative evaluated, I have a function of n, and now I let n go to infinity. To integrate 1 over x squared, you write that as x to the negative 2. You add 1 to the power, divide by the new power, and you get a negative x to the negative 1. And we can write that as minus 1 over x. So the limit I'm going to compute is the limit as n goes to infinity of the negative 1 over x evaluated from 1 to capital N. Put the n in first, then I subtract what I give and I put the 1 in. So we're going to take the limit as n goes to infinity of negative 1 over n minus a negative 1 over 1. Can you tell me the value of that limit? It's just 1. 1 over a very large number goes to 0, right? So that's 1. There's 1 square unit of area underneath that unbounded curve. So we say that that integral converges, and it converges to 1. Okay?
So n always has to be like a variable. We cannot say like n by 3 or 4.
Right. It's going to be a variable so that we can take this limit out here. Okay? You got to be able to move it after you take the antiderivative. So do the same problem. Take the squared off of the x. Make it just x to the first power. The graph is essentially the same. 1 over x looks a lot like the graph of 1 over x squared. Maybe it's not as tight to the x-axis, but it looks about the same. Integrate this now, and you get a totally different result doing the same steps. Integrate from 1 to infinity 1 over x dx by rewriting that as a limit. This time the integral gives me a logarithm. Those are both positive numbers. When I substitute in there, I don't need the absolute value bars anymore. I really don't even need to write the natural log of 1. What's the natural log of 1?
0.
0. Natural log of 1 is 0. So I need to know what the limit as n goes to infinity of the natural log of n is. What do you think? No idea?
Doesn't it get like infinitely big?
Yeah, the logarithm is a growing function. It looks like this. As I continue to move down the x-axis, it's getting taller and taller and taller. So that's going to infinity. So this integral diverges. There's exactly 1 unit of area underneath y is equal to 1 over x squared, exactly 1 unit. Increase this just a little bit to 1 over x, and there's an infinite number of area. Isn't that bizarre?
Is it because it's not as close to 0?
It doesn't get as close. It has to get asymptotically close to the x-axis, but it has to get dadgum asymptotically close to the x-axis. Yes, sir?
1 over x cubed also. 1.
Because 1 over x cubed is going to be underneath this one, right? So if you have a function that's bounded in area by a finite number, then it too will be bounded by a finite number. It won't be 1, because what's the integral of x to the negative 3? It'll be x to the negative 2 divided by negative 2, so you're going to get a factor of a half out here. Right? So you're going to get half a unit of area. So if I can squeeze graphs underneath the x squared, then they're going to have finite area. If they're above the 1 over x, they're going to have infinite area. Well, are there numbers between 1 and 2 that maybe would give me finite area? In other words, what's the lowest power or biggest power? I don't know which way to state it. What's the biggest power I could put here so that I have finite area? Let's do it. Let's just put a letter there, put a P there, and figure out what that power needs to be so that this integral converges. So that's my next question. For what values of P will the integral from 1 to infinity 1 over x to the P dx converge? Converges for x squared, diverges for x to the first. So a number in between 1 and 2 would be like 3/2. Let's see, let's just check. Let's just do this in terms of P. Let's rewrite this as the integral from 1 to n Move that up as x to the negative p. And then we're going to run the limit as n goes to infinity. So p is some number other than 1, because I want to be able to use the power rule. Add 1 to the power, divide by the new power. And then we're going to put the bounds in for x. This is just a constant. I'll pull it out. If I put the n in there, and if I put the 1 in there, 1 to any power is 1. So what kept this from converging was that this wasn't in the denominator. A log of n grows. We need this power to be of the quality that lets me simplify that to a 1 over x to the something. So when it sits like this, we need that entire exponent to end up as something negative. So we'll get a 1 over x to the something. So if minus p plus 1 is a negative number, then I can write that as a 1 over n-ish, and then that fraction will go to 0, if that's a negative number. And so if I solve this for p, that tells me that my integral is going to converge as long as that power is a number bigger than 1. If that power is 1 or smaller, it's going to diverge. 1 over the square root of x from 1 to infinity will diverge. But 1 over x to the 3/2 will converge. So there's our answer. So it diverges for p less than or equal to 1. Okay? P is bigger than 1, then that number plus 1 is going to be a negative number. We can flip the base. When n's on the bottom of a fraction and the constant's on top, that fraction goes to 0. So that's the motivation for that. We'll use that again and again and again in chapter 8. So let's look at some other functions that we have other than x to a power. Let's find each of the following. Nothing magical about the 1. I can move down the number line. I can go all the way over to 8. But x to the negative 2/3 is the same as 1 over x to the 2/3. What do you think is going to happen to the integral of 1 over x to the 2/3?
It'll diverge.
It should diverge. So go ahead and put the n there in the limit, do the integral, and convince yourself that this integral is going to be infinite. Go ahead and put this little pesky step in here. An extra fun problem when you have 8s and infinities and your hand gets all confused. Which way does the 8 go? So it's 2 steps from here. You integrate x to the 2/3, and you get, what, 3x to the 1/3? And x to the 1/3 is a growing function again. So I have 3 times the cube root of n. Cube root of 8 is 2, so minus 6. But n to the 1/3 is growing, right? N to the 1/3 looks something like this. It's a growing function as n goes to infinity. So this is infinite angle divergence. Okay? In each of the following, the question is converge or diverge. If it converges, find its value. And if it diverges, tell me why. So for the first one here, let's integrate from 0 to infinity. Let's go to minus infinity. Let's go from minus infinity to 0 of e to the 4x dx. So this time you put your letter down at the bottom and let that letter go to minus infinity. So even if this step seems a waste of time to you, let's put it in. Then find the antiderivative as a function of n and see if you know how to take that limit. find out? You're not sure, huh? Never done these before. What's the integral of e to the 4x? 1/4 e to the 4x. We have to evaluate that from n to 0. 0 goes in first. E to the 0 is 1. So 1 times 1/4 gives me 1/4. Now I put the n in. And I have that. So n is going to a very big negative number. So this is a big negative exponent. E to a negative power is the same as 1 over e to that positive power. So what happens to 1 over e to a positive power as that power gets bigger and bigger and bigger and bigger? Close to 0. For a limit, we're going to say it's equal to 0. So this is going to go to 0. Also think of the graph of e to the x. E to the x looks like this. If I'm way back here, this is getting real close to the x-axis. As n goes to minus infinity, e to the n goes to 0. As n goes to plus infinity, e to the n goes to infinity. In other words, e to the infinity is infinity, e to the minus infinity is 0. So that goes to 0, so this converges to 1/4. Okay. So we're talking about functions here that have some version of an asymptotic behavior. So my next example has the integrand of 1 over the square root of 4 minus x squared. In order to compute this improper integral, we've got to replace the infinity symbol, make it a proper integral. So I'm using an n again. And see if you know how to compute that. What is that integral? You know this one? You recognize it? No one love it? That's one of the arcs. An arc, which one? That's an arc sine. So this one's just the arc sine of x over 2. Evaluate from 0 to n. So we have the arc sine of n divided by 2 minus the arc sine of 0. But I bet you know the arc sine of 0 is 0, since the sine of 0 is 0. So what we're going to do is figure out this bit here. That makes absolutely no sense if you know what the graph of the arc sine looks like. Does anybody know what the graph of the arc sine looks like? Well, it doesn't even have an infinite domain. The arc sine takes numbers between -1 and 1 and gives me angles between minus pi halves and pi halves. Right? The arc sine is a function whose range is between -1 and 1. It looks something like this. Let's see, the arc sine of -1, sine of negative pi halves is -1. It looks just like this, no arrows on the end of it. So if n is way the heck out here, there's not even a graph out there. So the value is not infinite. There's no such thing. This is not a entity that has an infinite limit, but it doesn't have a finite limit either. This limit does not exist. Okay? There's no graph of this function out there. It truncates. But now let's take the square root sign off and put plus in between. Let's look at this one. It's another one of our inverse trig functions. So if we block that off from 0 to n, we can compute that. Which inverse trig function is that one? That's the arctangent. So we get 1 over 2 arctangent of x over 2. And so I put those numbers in. The arctangent is a function that takes numbers from -infinity to infinity and maps them to numbers in a certain range. So think about the graph of the arctangent by referring to the graph of the tangent. Do you know what one period of a tangent function looks like? Kind of like an x cubed type thing, but it has vertical asymptotes. Can you give me some adjacent vertical asymptotes of the tangent function? Tangent is sine over cosine. Where's cosine 0? The pi halves-ish, right? So when we define the arctangent, we limit the domain of the tangent between negative pi halves and pi halves as the x values. Those become the y values on the arctangent. So the arctangent has horizontal asymptotes at negative pi halves and positive pi halves, and then does its little squiggly thing in there. So here's the graph of the arctangent of x. Goes through 0, so that's telling me that this number is 0. But the things that were the vertical asymptotes for the tangent function become the horizontal asymptotes for the arctangent function. This one would be positive pi halves, and this one's negative pi halves. So the picture's telling me that when n goes to infinity, this arctangent graph climbs to pi halves. Similarly, if I ask you what happens if n goes to -infinity, the graph goes to negative pi halves. So we're going to put this in your head, that the arctangent at infinity is pi halves, and the arctangent at negative infinity is negative pi halves. So this becomes pi halves times a half. So this one converges to pi over 4. But what this little asymptotic behavior on both ends allows me to do for this particular example is I can integrate from minus infinity to positive infinity. But let me show you how to do that. That's not as easy as just plugging those numbers in. Let's do the same problem, but integrate from minus infinity to positive infinity. In order us to be able to do these limits, we've got to break up the number line somewhere in between and then write this as two integrals. So I think the logical place is to integrate from minus infinity to 0 and 0 to infinity. This function inside here is a continuous function. I can use that linearity rule. And then what I do is I replace this with a letter and let that letter go to minus infinity and then do the same stuff over there. We use different letters. We got a whole alphabet. Let's take the limit. Let me put an M here. And let M go to minus infinity. And then I'll just redo the other problem that we did a second ago. Put an N there. Let N go to plus infinity. We already know this. We did these steps. That goes to pi fourths. So let's do those steps over there. So we'll call that star. We'll do star's calculation right here. We get the limit as M goes to minus infinity of 1 over 2, the arctangent of x over 2, evaluated from M to 0. Put the 0 in for x, put the M in for x, and subtract. And the arctangent goes through the origin, so the arctangent of 0 is 0. Now let's think of the picture I just erased. M is going to minus infinity. Divided by 2, it's still going to minus infinity. Arctangent toward minus infinity does what?
Negative.
Goes to negative pi over 2. So that part of the integral also goes to pi over 4. So this integral up here looks like pi over 4 plus another pi over 4. There's pi halves, total units of area under that curve. Do you know what the graph of this looks like? It behaves like 1 over x squared, but on both ends, and there's no disconnection. If you were to graph this thing, you would get a bell-shaped curve. Where are bell-shaped curves used? In statistics. The normal distribution is of things that are normally distributed follows the behavior of bell-shaped curve, and in statistics that represents something called its probability density function. And one of the properties of a probability density function is that the area under the curve gives the probability that an outcome is between such and such. So the total area under the curve has to be 1. So if you scale this down so that the total area under the curve is 1, you'll have the bell-shaped curve for the normal distribution. And so those of you engineering students that have to take 3342, you'll see that again. Okay, now I'm going to do another calculation. Let's see. Let me rub some of this stuff off here. I'm going to take another hyperbola here. All right, if u is x minus 2, du is dx. So I'm integrating 1 over u squared. The integral of 1 over u squared is negative 1 over u. I don't know, so how about we evaluate this from 0 to 3. So I evaluate that from 0 to 3, and I get negative 1 over 1. Put a 0 in there, and I get a negative 1 over negative 2. So I get 1 plus a half. I get a negative 1/2. Right? All good? Did I do all that right? Oh, I get negative 3/2, right? So that doesn't change the sign. I get a negative 3/2. Well, that's even worse. I took something that's clearly positive and above the x-axis, right? 1 over something squared has to be above the x-axis. I took a positive curve, found the area underneath it, and I got a negative number. Why is the area under a positive curve a negative number? You're checking my algebra, weren't you? Somebody tell me what went wrong. I'm not running to Home Depot and saying I need negative 3/2 square feet of tile. Nobody sees a problem, then I guess we do have negative area. It's got an asymptote. Big old rip in that graph between 0 and 3. Where's that rip occur? Yeah, area is negative when part of the graph is under the x-axis, right? So we always accommodate for that by taking top graph minus bottom graph. Well, this graph flips across the x-axis when x is 2. There's a vertical asymptote or a discontinuity when x is 2. These sequence of steps apply only for continuous functions. I can compute definite integrals when this is a continuous function. over that bound. This is not a continuous function on 0 to 3. So none of these steps are valid. Discontinuous, continuous, CONTINOUS. Fundamental theorem of calculus says the integral from a to b of f of x dx is the antiderivative of f at b minus antiderivative of f at a, provided the integrand is a continuous function. So I can't do any of those steps. This is an example of a type 2 improper integral. So let me write down in general what a type 2 improper integral looks like. The integral from a to b of f of x dx is a type 2 improper integral if f at a is infinite, or if f of b is infinite, or f of c is infinite, where c is some number between a and b. If it has a discontinuity at the lower bound, at the upper bound, or at some number in between, like here. So we're talking about the expression in the integrand. So those are typically things that look like fractions. This one had a discontinuity where the denominator is 0.
The stretch break.
Stretch break. We're just plowing. We're just rolling and going. Because I had like the extra hour today. Okay, go stretch. It's like when you get stuck at a party talking to somebody that you don't want to talk to. You just give him that look to your husband saying, "Get me out of here."
I realized I forgot to put a plus C on one of my phones.
Oh, that's no big deal. I won't let go for a plus C. No problem with a plus C. It's just $1 for each plus C. You guys want to stretch? I want to sit down. Then I won't get back up.
It's getting a little empty.
You guys aren't stretching. You're getting all that collection of blood in your locus.
That's fine.
Bring a little ball in here. Have a good game of volleyball or something. The people at home don't have to stretch because they went to sleep about an hour ago. Isn't that right, guys? You guys are asleep, aren't you? You can't see what I'm stretching. Well, I've got this visual. That must mean Jacob's asleep.
midterms.
What do you say?
I said, did y'all have midterms this week?
Yeah, I have like a physics test plan.
And stat, physics and stat.
I think my top 2 midterm, this midterm, it's the day before my midterm. I have a Spanish midterm next week.
Well, I have a chemistry today.
Chemistry,
Yeah, tonight actually.
Yeah, they make you take your test at night. Why can't I get away with that?
oh, Chem 1, right?
Yeah.
I don't know why Kim does that. Make us take it at like 9.
So they only have to make up one test for everybody.
That makes sense.
Plus, this semester is like last time. We're still gonna have class today. With new content. And we have a test tonight.
Wow.
Wow, we're talking about midterms.
Well, I did that last time.
Yeah, it's just like it stinks living in the dorm because like my roommate has Kim at like 7:30, so I have to like find a place to be.
Oh, because she's taken her test or, interesting.
Yeah, because it's like it's through Proctorio, and so
Yes.
you can't have anybody else like
Wow.
around
Well, come to my house. I'll feed you and we'll do calculus. Well, I shouldn't threaten to feed you. That's enough to keep you away. Or the do calculus part would keep you away too, wouldn't it?
You're gonna help me with my homework.
I can help you with your homework.
Did you run out of contacts or are your eyes dry?
I just was giving them a break.
Whenever I stay up really late the next day, I can't wear my contacts.
And I have to with everything else.
I did this case second. It's a little bit more difficult. It has more steps. Not difficult, more tedious than the other case.
That means more than.
Not really. We still need the same thing to happen. We need the graph to hug the discontinuity tightly. But this time our discontinuities are this way. So we've got to get the graph to hug it tightly in that direction. If it doesn't hug tight enough, then the integral is not going to exist. So we have to have all kinds of knowledge about the behavior of these functions near certain values and when x gets big or small. Are we done breaking?
We should break till next Tuesday.
This one.
Good thing you have a mask so I can't tell who said that. I'll try to let you out a little early. Okay, so here are some functions that have discontinuities at x is equal to 1. Let's see why they behave different. So each of the following functions, integrals, involve functions that are not continuous at x is equal to 1. The first one is the integral from 0 to 1 of 1 over x minus 1 to the 1/3. The second one is the integral from 1 to 4 of 1 over x minus 1. And the third one is the integral from 0 to 1 of x over 1 minus x squared squared. And x is equal to 1 is the only discontinuity of each of these, because it gives me 0 in the denominator. So all three of these are improper integrals of this type 2 nature. So we kind of do what we did before. If one of the bounds of integration is the discontinuity, stick a letter there, and then run the letter, in this example, to 1. So typically I call my lower limit A and my upper limit B. So I'm going to rewrite this integral from 0 to B, and then I'm going to take the limit as B goes to 1. But it's going to be a one-sided limit. On the number line, here's 0 and here's 1. I'm putting B to be right here. So B is coming into 1 from the left. In the next example, I'm going to put an A as the lower limit. I'm going to integrate from A to 4 of 1 over x minus 1. And I'm going to take the limit as A goes to 1. But this time my integral describes the number line from 1 to 4. So A is over here, and I'm going to come into 1 from the right. I'll save my big M and big N with M and N go to infinity, and I'll use A and B's for the discontinuities. Okay, how do you integrate 1 over x minus 1 to the 1/3? U du, U is x minus 1, du is dx. So I'm integrating U to the negative 1/3. So we're doing the power rule. You add 1 to negative 1/3, you get a positive 2/3. Flip and multiply, you get 3/2 times U to the 2/3. So U is x minus 1. We're going to take the limit as B goes to 1 from the left of 3/2 of x minus 1 to the 2/3 from 0 to B. B goes in first, and we get the expression B minus 1 to the 2/3. Then we put the 0 in there, and we get negative 1 to the 2/3. All with the 3/2. So B minus 1 to the 2/3 minus 3/2 of 0 minus 1 to the 2/3. So that last parentheses holds a negative 1 to the 2/3 power. The 2/3 power is a cube root, then squared. So the cube root of negative 1 is negative 1 squared, and I get positive 1. This number out here is just 1, so I just get 3/2 out of this. Now let's figure out what happens there.
It gets closer to 0.
It's close to 0. That limit is 0, right? We can compute these one-sided limits just by imagining that we're substituting 1 in here, and 1 minus 1 gives me 0. 0 to 2/3 is 0. So you get 0 minus 3/2. This integral converges to negative 3/2. On the interval from 0 to 1, this is not a positive function. It's negative because that graph is under the x-axis. Bless you. Okay, so there's an example of a type 2 convergent improper integral. Bet you $1 that's a divergent improper integral. Because what's the integral of 1 over x minus 1? It's the natural log of x minus 1. So this integral, we're going to take the limit as a goes to 1 from the right of the natural log of the absolute value of x minus 1 as x varies from 4 to a. So we look at the limit as x goes to 1 from the right sorry, not x, a goes to 1 to the right. When I put a 4 in there, I get the natural log of 3. When I put an a in there, I have the natural log of a minus 1. So again, as a goes to 1, a minus 1 goes to 0. What's the behavior of a natural logarithm near 0? Negative infinity. So this part behaves like negative infinity. So when I subtract negative infinity, I'm getting a large positive number out of this. So this integral diverges. They're very similar functions. 1 over x minus 1 and 1 over x minus 1 to the 1/3, that's a hyperbola. Both of them have the discontinuity at x is 1, and they both kind of look like this. But one of them gets closer to this discontinuity than the other one does. Oops, 0 to 1. I want to go here. So when x is 2, y is 0. It does this way. 0 to 1. Give me my 0. There's 1. 0 to 1. That one's down here. The other one's up here. So from 1 to 4, that's not close enough. 0 to 1, that one is. Both have that same graph, but one's tighter than the other one. So set up the third example so that you have a well-defined definite integral. The discontinuity is again at 1. Compute that definite integral and then take the limit as whatever letter you use goes to 1 from whatever side you say. Let me see you try that third one all by your lonesome. Anybody got it converging? That's a good sign because it doesn't converge. It's a UDU integral, right? Take away the discontinuity by sticking a letter there. That's at the top, so I'm going to use a B. I'm coming in from the side of one that occupies 0, so I'm coming in from its left. Now I can do that integral with the UDU. If u is equal to 1 minus x squared, then du is a negative 2x dx. So I'm going to get a negative 1/2 du for the x dx. And so that particular integral has a negative 1/2 integral. Let's write that as u to the negative 2 du. And the integral of u to the negative 2 is minus u to the minus 1, or negative 1 over u. So this now becomes positive 1/2 times 1 over u. So the limits that we have to evaluate, as b goes to 1 from the left, involve 1/2 times 1 over 1 minus x squared, evaluated from 0 to b. Over here. So when I put a b in there, I get the 1/2, 1 over 1 minus b squared, minus 1/2, and I'm putting 0 in there, and I just have a 1. So we still have the problem that I still am dividing by 0 when I take my limit. So because of this term is still in the denominator, 1 over 0 gets infinitely large. And that didn't do anything to it. So this integral diverges. So maybe what you see is that I need, after I take the antiderivative, to not have a denominator anymore. Right? And the integration involves adding 1 to the power. So in order to not have a denominator anymore, well, this one didn't have a denominator, but it had a logarithm. Right? Look at the powers. Typically, what kind of power do you need in order to get rid of that kind of discontinuity?
Less than or equal to 1.
Looks like it's going to have to not even equal to 1. It's going to have to be less than, because if equal to didn't work. We need a small enough number here so that when we move it upstairs and add 1, we get something to a positive power. So kind of the opposite situation that we had for infinite balance. So I want to show you what happens when the discontinuity is in the middle, like in that other example, and then I'll probably let you go. Unless you want to stay. So, let's rub all this off. What was that example I did? I did the integral from 0 to 3. Oops, I don't want limit. I did an integral from 0 to 3 of 1 over, what was it, x minus 1 squared? So my discontinuity is inside. So I got to make 2 problems out of this. I'm going to integrate from 0 to 1, and then 1 to 3. And then I'm going to remove the discontinuity at 1 by sticking a letter in there. the same kind of logic that we used when we broke up the infinite, minus infinity to infinity integral. Find an in-between point. Here the in-between point is our discontinuity. Rub out that discontinuity with a limit. So I'll put a b for the top limit. Let b go to 1. It's coming in from the 0 side, so it's coming in from the left. Put a as a lower limit. From a to 3. And then run a to 1 from the right. So we did some version of that already from 0 to 1. Right? We did something squared. We get the same antiderivative. We're going to get the 1 over the u term. So here again, we're integrating u to the minus 2 du, so we get a negative 1 over u from 0 to b. Take the limit as b goes to 1 from the left. Same deal here. But in either case, if b is going to 1, I'm going to get a 0 in the denominator. Zero in there, and I get 1. So that's this one. But this limit does not exist. It goes to minus infinity, right? Same deal here. This limit does not exist. One minus, oops, that shouldn't have been there. That should be a 3. 3 minus 1 is 2. So this also doesn't exist. Right? That's infinite. So this diverges. So each one of these gives me dividing by 0, which is why that limit doesn't exist. It becomes infinite. Okay? So just like before, we need some sort of power here, though, to be smaller than 1 for these steps to give me a limit that exists. Okay, everybody? So what you gotta do is recognize where the discontinuity is before you start integrating. Otherwise, you'll make the blunder that I did at the beginning and said that that integral is negative 2/3, and it's not. Okay? Pay attention. It's easy to pay attention when you're isolated on that section. When I mix them in with problems that we've been doing, you're going to be on the ball. Okay? So I put the harder integration problems on web work. I did all the easy ones for the example. You'll get to integrate by parts and stuff like that. Save all the fun for you. Okay, so I'll let you go if you want to go. Get you through your little break. And give you 12 minutes here. If you have homework questions, I can answer your homework questions.
Yeah,
You got homework. Thank you. Well, that's in the stack that I didn't grade last night. I did a little grading on my phone. I pulled up a problem and I graded it mentally. Thank you very much. I can find it. Doesn't that look weird?
Mine look weird.
Yours always looks weird. No.
I'm just talking about the big space at the bottom. So I know that's not going to be.
I should have given you more problems then.
Dr. Schovanec,
Yes.
so the answer does not exist.
That's right. There's no limit. The limit's infinite. So this question would be it diverges.
Oh, so it
Right.
diverges.
It diverges because the limit is infinite,
Okay, got
right?
Yeah.
A limit that's infinite typically doesn't exist. Your web work will ask you sometimes, is it going to plus infinity? Is it going to minus infinity? Or like with that inverse tangent, or I'm sorry, the inverse sine, it didn't exist because there's not even a numerical value
Yeah,
associated with it.
out of the main.
So this is one that becomes infinite.
Okay, thank you.
Bye, thank you. All right, questions, anybody? We can't see the half of that board there. Let me see.